everyone, and thanks for watching Edupedia World videos. In this video, we begin our understanding of logical variables and logical functions. Now, what is a logical variable? A variable which can only assume one out of two values is called a logical variable. Let's say if x could either be 0 or 1, then it would be a logical variable. A switch can either be on or off, right? It cannot be midway off or midway on. It is either on or it is off. So a switch may be a logical variable. A function of logical variables is called a logical function. And a logic gate is an electronic circuit which evaluates a particular function. An electronic circuit which can evaluate a logical function. So the moment I say logical variables or one of two values, immediately you should probably start thinking binary numbers, because binary numbers are the quintessential logical variables because they can take a value of 0 or 1. And whenever you have a complicated machine, let's say even a calculator which adds two numbers, what happens is both the numbers are first converted into binary, and those two binary numbers are added using electronic circuits which can actually evaluate functions of those two binary numbers, in this case the sum function, and then give you a final value using the logic gates, the electronic circuits which is in the calculator, and the final value is then finally converted back from the binary numbers to the decimal numbers, and then you get your sum of two numbers. Right. So let's start with our studying of logical functions. There are three basic logical functions which we'll see in this video and two in the next video. The first one is called the AND function. Now a function has to have variables, and AND has two variables. Let's call those variables A and B. So when A and B are joined together using the AND function, it's either written as A dot B, or sometimes it's simply written as AB. So A dot B or AB means A and B. Now AND has a particular set of values for each value of A and B. A can either be 0 and 1 and B can be 0 and 1. So A and B together can either be 0 0, 1 1, 0 1 or 1 0. That means the AND function needs to have its value specified for 4 different combinations of A and B, and this particular realization of the value for 4 particular combinations is called a truth table. So let's draw the truth table for A dot B, or simply AB. So this is A, this is B, and let's say this is C, which is equal to AB. Either they can both be 0, or it can be 0 and 1, or it can be 1 and 0, or 1 and 1. Now the good thing about these basic logical functions is they are really characterized by the words which we use to describe them, such as the AND function. So 0 and 0 would give me 0. 0 and 1 would also give me 0, because if both of them were 1, then we would say the AND is true. 1 and 0 is also 0, but if you have both of them true, then the answer is 1. So C is equal to A and B is 1 only if A and B both are 1. Right, we'll see the same thing again a little bit later when we do the OR function, in which case C is equal to A or B will be 1 if either A or B is 1. So it's pretty nicely served by the definition, and that is why we actually call it the AND function. This is the truth table for the AND function. If both are 0, it is 0. If either one of them is 0, it's still 0. Only if both of them have a value 1 is it equal to 1. The symbol of the AND gate in logical circuits is this: A, B, and this is the symbol for the AND gate, and this is C. So whenever you see this symbol, it just means C is the result of A and B. Now we can actually realize this function using an electronic circuit, using diodes as a matter. We'll need two PN junction diodes, and in these cases, whenever we use a PN junction diode, or later we'll use a transistor to try to create logic gates, we have a convention which we use, which is a potential of 0 volts is taken to be the logical variable 0, and a potential of positive 5 volts is taken to be a logical value of 1. V is equal to 0 is 0, V is equal to plus 5 is 1. This is C, and both of these are connected to a resistor, and the resistor is connected to a 5 volt battery, and the battery is connected to the ground. So this is 0 volts, this is 5 volts. This is A and B. What would happen if A and B both had a value of 0? In that case, both these junctions would be forward biased, and current will flow from this direction to this side, and since all these are wires, this is the only place where the potential difference would be. The potential here would be the same as here, which would be 0. What if B had a potential of plus 5 volts? In that case, there would be no current flowing through B, but the current still would be flowing through A, and since this is still short circuited, this would have the same potential as A, which would be 0. Similarly, 1 0 would give 0, but what if A and B both had a potential of plus 5 volts? In that case, there would be no current flowing through either of these wires, there would be no potential difference across this resistor, and the potential of C would be the same as the potential of this point, which is positive 5 volts, or a value of 1. So we do realize indeed the truth table of C is equal to A and B if we take this type of a circuit. The next logical function we'll see is the OR function. These are sometimes also, the functions themselves are sometimes also referred to as gates or logic gates. So OR, I'll just draw the truth table first. It is shown as C is equal to A plus B. A into B is AND, A plus B is OR. And if this is 0, this is 0, this is 0, if either A or B is 1, or indeed both of them are 1, in all three cases it is equal to 1. Right. And the symbol for the OR gate is something like this. This is A, this is B, this is C, equal to A plus B. So either A or B or even both of them have to be 1. In that case, C is equal to A or B is 1, but in all other cases, C is equal to A or B is 0. Right. Let's try to realize this using PN junction diodes again. So in this case, all we need to do is switch the polarity of the PN junction diodes and remove the 5 volt battery. This is C, this is A, B, and they're all connected to the ground. So this is 0 volts. What would happen if both A and B are of 0 volts? Then there would be no current flowing, and in that case this would obviously be 0 volts again. So A and B 0 gives 0. What if B was at a potential of plus 5 volts? In that case there would be current flowing. Here there should be a resistor, my bad. So if B was 5 volts, then there would be a current flowing through this diode because it would be forward biased, and since this is short circuited, the potential here would be the same as the potential here, which would be 5 volts. So C would be equal to 1. If B was 0 but A was plus 5 volts, still there would be a current flowing through this wire, and this would still have a potential of 5 volts. If this has 5 volts, this is 0, no current is flowing here because it's reverse biased. And if both of them have a potential of plus 5 volts, that means both of them have a value of 1, then there's current flowing through both the PN junction diodes, and this would still have a potential of 5 volts. So we see that if we remove the battery and take the direction of reverse the direction of the PN junction diodes in both cases, we go from the realization of an AND logic gate by an electronic circuit to the realization of the OR logic gate by an electronic circuit. Now both these circuits, both these logical functions take two variables, A and B, and A and B are either ANDed to get C or ORed to get C. But this is a third type of logical function, the NOT function, which only takes one variable. And the symbol for the NOT function is this. If this is A, the NOT function is B, which is also symbolized as A bar. A bar means not A. And the truth table is pretty clear in this case. If A is 0, not A is 1, and if A is 1, not A is 0. However, this cannot be realized by a PN junction diode, and we actually need a transistor to realize the NOT gate. So the transistor can be used to realize the NOT gate, and this would be A, which would have a current in front of it. Then you would have a transistor like this, and this would be attached to B, and this would also be attached to a resistor, and there would be a 5-volt battery plus 5V. Right. So now let's assume that A is 0. If A is 0 and this is 5 volts, then this junction is reverse biased and no current will flow here. So if A is 0, there will be no current through this circuit, and this will have a potential of 5 volts, the same as here. So it will be 1. If there is a current through A, then this will not be reverse biased anymore. There will be current flowing through this, and then since this whole thing is short circuited, the potential then would be 0. The only potential differences in all these three cases will be across a resistor. So in that case, if A has a potential of plus 5 volts, then B will have a potential of 0. So this is the realization of the NOT gate using an electronic circuit. So these are the three basic logical functions, and now we'll look at three more logical functions which are somewhat advanced. The first one of them we'll see is the NAND gate. The NAND gate is basically the NOT AND gate. So you have A and B, and first of all you take A and B, and then you put a NOT in front of it. So the opposite of A and B is C. So the truth table of the NAND gate is pretty simple. You just take C is equal to A and B, and then you just invert it. So if this is A, this is B, this is AB, which is A and B, and this is C is equal to NAND B. So 0 0 0 1 1. A and B is 0 0 0, and only in this case it's 1. So NAND B is 1 1 1 and 0. Right. So this is the NAND gate, and the next one we'll do is, again, you guessed it, the NOR gate. So the symbol for the NOR gate is, you do A or B and then you put a NOT over it. So C is equal to NOT of A or B. So this is A, B, A or B, and this is C is equal to NOT of A or B. 0 0 0 1 1 0 1 1. So 0 1 1 1 was A and B, so this will be the opposite of that, was A or B, so this will be 1 0 0 0. You don't really need to remember these truth tables. I just remember AND and OR, which are simple enough, and then NOR is just NOT of OR, and NAND is just NOT of AND. Now there's one final one that is called the XOR gate, or it is sometimes called the exclusive OR. And the symbol is this. It's like the OR gate, but there's an arrow before the OR gate as well, a curve before the OR gate, and this is C. Right. And there's no specifically symbol for it. It is sometimes written as A XOR B, but it is equivalent to A B bar plus A bar B. Right. So A and not B, or not A and B. So let's see what the truth table would be. A, B, C. If both of them are 0, then obviously A and B, A and not B would be 0 and 1, which would be 0. And again, not A and B would be 0, and 0 and 0 would be 0. Let's take 0 and 1. So not B now would be 0, 0 and 0 would be 0. Not A would be 1 and B would be 1, so both of them ANDed would be 1, and 1 OR with something is 1, so this is 1. Similarly, you can verify that this will be 1, and if you have both of them 1, then A and not B will be 1 and 0, which is 0, and this will be 0 and 1, which is 0, and 0 or 0 is 0. So if A and B are different, then it is equal to 1, and if A and B are the same, whether it's 0 or 1, then it is equal to 0. Right. So now these might seem a little bit arbitrary to you, but now we get to actually the use of it, and we'll just look at the very basic use, the addition of two binary numbers, and we'll see how that can be accomplished by using these 6 gates. So the most interesting gates actually are the NAND and the NOR gates, because they are sometimes called the basic building blocks of logic circuits, because all other gates can be created using NAND and NOR gates. So first I'll show you how. Let's look at the NAND gate first. How do we create the AND gate using just the NAND gate? And I'll just draw the figures. You can verify that on your own, that these actually come out to give the correct truth tables. So you take A and B, and we'll just be using the NAND gates. That's the beauty of it. So you do this, this is A NAND B, and then you just take that in both the terminals of another NAND gate, and that will give you C is equal to A and B. Because they'll be the same, and you have two things the same, then it will be 0 or 1 based on whatever this thing is, and the NOT of that will be the opposite. So this is sort of like a NOT gate. The OR gate can be constructed like this. You take A and NAND it to itself. You take B and NAND it to itself. And you take these two and then you NAND them together. And that will give you C is equal to A plus B. And for the NOT gate, you just need one A, and all you need to do is NAND it to itself, and you will get C is equal to A bar. So this is how you can actually create these 3 basic building blocks, and after you have AND, OR and NOT, you can create any building block, any logic circuits, including the exclusive OR. Now let's look at how you can create all 3 of them using the NOR gate. So to create the AND using the NOR gate, I would like you to verify these on your own. So you take A, you NOR it with itself, you take B, you NOR it with itself, that is A NOR A and B NOR B, and you NOR them together. Sorry, this should be the NOR gate. And this will be C is equal to AB. You want to do the OR gate, you take A and B, you NOR them together, and then you NOR that thing to itself, and you'll get C is equal to A plus B. And if you want the NOT gate, that's the same as in case of the NAND gate. You just take A and you NOR it with itself, and that will give you C is equal to A bar. So we've basically seen how you can use these 3 gates to construct complicated gates, but you can use the more complicated NOR and NAND gates and use only those gates to actually construct the AND, OR and NOT gates, and that's why these are called the basic building blocks of logic circuits. In the next video, we'll actually see how you can use these functions to add 2 numbers using an electronic circuit, which is the basic principle of the simple calculator. Thank you.